Hello and welcome to this video for OCR A-Level Physics on the Forces in Motion module in the topic of Newton's law and momentum, looking at the concept of Newton's third law. So if we've been successful and we've learned in today's lesson, we should be able to define and describe Newton's third law of motion, detail Newton's third law pairs, and calculate values based on Newton's laws of motion. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification. 3.5.1 Newton's laws of motion. Now when two objects interact, each exerts a force on the other. Now Newton's third law says that these forces are equal and opposite to each other. So this leads to the following Newton's law of motion. When two bodies interact, the forces they exert on each other are equal in magnitude and opposite in direction. Now these two forces are sometimes described as an action and reaction, but this is quite misleading as it sounds as though one force arises as a consequence of the other. In fact, the two forces appear at the same time and we can't say that one caused the other. Now you can hear this law as every action has an equal but opposite reaction. Now this isn't a good way to describe this law as it implies that the forces are both applied to the same object. Now if this was the case, then you will get a resultant force of 0 and inertia for all objects. Now the two forces which make up a Newton's third law pair must have the following characteristics. They must act on different objects. They must be equal in magnitude. They must be opposite in direction, and they must be forces of the same type. So for example, two objects may attract each other because of the gravity of their masses, so it would be two gravitational forces. For example, two objects may attract or repel each other because of their electrical charges, the electrical force. Two objects may touch each other, so contact forces. Two objects may be attached by a string and pull on each other, so tension forces. Or two objects may attract and repel because of their magnetic fields, being magnetic forces. Now the two forces in Newton's third law of motion represent the same interaction seen from two different perspectives. So for example, if you push against a wall, the wall will push back against you just as hard. When you stop pushing, so does the wall. If you pull a cart, whatever force you exert on the rope exerts the exact opposite pull on you. When you go swimming, you push back against the water with your arms and legs, and the water pushes you forward with an equal sized force. Now Newton's third law applies in all situations and to all types of force, but remember, the pairs of forces are always the same type of force, have the same magnitude and act on different objects. So sometimes it looks like Newton's third law is being applied, but actually it's not. So you must be very careful when trying to work out if forces are Newton's third law pairs. So consider a person standing on the surface of the Earth. Now the two gravitational forces observed in this diagram are a Newton's third law pair, as are the two contact forces. But do not be misled into thinking that a person's weight and the contact force of the floor or the earth are a Newton's third law pair. Although they are equal and opposite, they do not act on the same object, they act on different objects, and they are not of the same type. So, as we said before, Newton's third law applies in all situations and to all types of forces. The forces must be of the same type. Now, like we said, sometimes it looks like Newton's third law is being applied, but actually it's not. So if we consider the gravitational force acting on the man and the contact force from the earth on the man, they are equal but opposite. So the resultant force is 0, so the man does not accelerate. However, because both forces act on the same object, it is an example of Newton's first law of motion, not Newton's third law of motion. So Newton's laws of motion can be summarized as the following. Newton's first law: the velocity of an object is unchanged unless a resultant force acts on it. Newton's second law: the acceleration of an object is proportional to the resultant force acting upon it, F equals ma. And Newton's third law: when two bodies interact, the forces they exert on each other are equal in magnitude and opposite in direction. Now there are many applications of Newton's laws of motion in the real world. Examples include in engineering, such as structural designs, where engineers use Newton's laws to design buildings, bridges and other structures. They analyse the forces acting on different components to ensure structural integrity. Transportation, understanding Newton's laws can help engineers design vehicles like cars, planes and spacecraft by considering factors like acceleration, braking and stability. And in mechanical systems, machines and engines rely on the principles of Newton's laws to function effectively and efficiently. In physics, in astronomy, Newton's laws explain the motion of celestial bodies, including planets and moons and comets. They form the basis of gravitational theory and help us predict and understand astronomical phenomena. And in particle physics, Newton's laws are fundamental in understanding the behaviours of subatomic particles in particle accelerators, allowing scientists to study the fundamental forces and particles of nature. In space exploration, rocket propulsion needs Newton's third law, as it allows the rockets to work because the ejection of high-speed gases generate a reactive force that propels a rocket forward. And in orbital mechanics, Newton's laws play a crucial role in calculating trajectories, orbital maneuvers, and planning missions in space exploration. So we can apply Newton's laws of motion to any situation in the universe, for example, riding the bus. So for Newton's first law, you'll get on the bus and stand up. When the bus is stationary, you feel no force. When the bus accelerates, you feel a backwards force. You want to stay where you are, but the bus forces you to move. When the bus is at a constant speed, you feel no forwards or backwards forces. The bus slows down and you feel a forward force. You want to keep moving at the same speed, but the bus is slowing down so you fall forwards. If the bus turns left, you want to keep moving in a straight line, so you're forced to the right. If the bus turns right, you want to keep moving in a straight line, so you're forced to the left. Newton's second law. As more people get on the bus, its mass increases. If the driving force of the bus's engine is constant, we can see it takes longer for the bus to gain speed. And finally, Newton's third law. As you stand on the bus, you are pushing down on the floor with a force that is equal to your weight. But if that was the only force acting, you will begin to move through the floor. So therefore, there is an equal but opposite force from the earth on you. There is also a normal force from the floor onto the human and from the human onto the floor. We can also look at the situation of taking a lift. With Newton's first law, when you get into the lift and when it moves at a constant speed, you feel no force up or down. When it sets off going up, you feel like you're being pushed down as you want to stay where you are. When it sets off going down, you feel like you are lighter, you feel getting pulled up. In terms of the second law, as more people get into the lift, its mass increases. If the lifting force is constant, we can see it takes longer for the lift to get moving. Or we can see that with more people, the greater the lifting force must be. And finally, with Newton's third law, as you stand in the lift, there's a weight downwards to the earth, but there's also an equal but opposite force from the earth to you. In addition, there's a normal force upwards from the floor to your feet, and there's a normal force downwards from the feet to the floor. So that brings an end to our lesson today. If we've learned in today's lesson, we should have a knowledge and application of the three laws of motion in appropriate situations, and know F equals ma for situations where the mass is constant. So if we've been successful and we've learnt in today's lesson, we can define and describe Newton's third law of motion, detail Newton's third law pairs, and calculate values based on the laws of motion. So thank you for watching this video on Newton's third law, which is part of the Forces of Motion module for OCR A-Level Physics in the subtopic of Newton's law of momentum. Thank you so much and have a lovely day.